Till last lecture, we have talked about the material properties, specifically the mechanical properties of materials. Now, these mechanical properties actually evolve if you look at it starting from the atomic structure itself, or let us say how the atoms are getting bonded, because there are certain ways in which the metals get bonded, there are certain ways in which the non-metallic systems or the ceramic systems get bonded. So, we will today go inside, deep inside this atomic bonding, and we will try to find out the answers for some of the reasons of the mechanical properties. Now, it must be said that not all the mechanical properties can be answered in terms of atomic bonding, because atomic bonding is just the very micro level phenomena at the smallest length scale, which affects undoubtedly the mechanical properties, but then from that scale, as we go towards suppose larger and larger scales, then many other mechanisms occur which also contributes to the mechanical properties of the system. So, let us start our journey from the atomic bonding level. Now, the issues that we will try to address in while talking about the bonding between atoms, because it is a very vast subject, but we will keep ourselves focused on what promotes bonding, that is very important, and what types of bonds or how many types of bonds are there, and which properties can be inferred from the bonding. So, let us try to look into these sorts of things. Now, you should always have a clear idea of the periodic table while discussing about it, because there are two very important things that happens if you look at the periodic table from the from our interest point of view, and that is that where the or how the electropositivity is changing. This is one thing, okay, and which actually talks about that how readily the atoms can give up the electrons, and just the counterpart, that how the electronegativity changes. That means, the capacity or the eagerness to acquire electrons, how that changes, and periodic table can very clearly tell you about it. Say for example, if we look at the leftmost corner of the periodic table, then we can see that this is the region where all these atoms can actually give one electron. Giving one electron is very easy for them. So, that means they are the top in terms of the electropositivity. Okay. They can anytime very easily lose that electron and become electropositive. So, for example, hydrogen is there, lithium is there, sodium is often referred as one of the most active material in terms of making compounds like sodium chlorides and all other things. So, they are very very active, and then you have potassiums, then rubidiums, calcium, and all these materials are there. Okay. So, that is the group or the column suggests that group which can become electropositive very fast. The next pastes are the group which can actually give 2 electrons instead of 1 electron. And the most important metals that come into picture, there are something like magnesiums are very important. Okay. And then even lesser degree of electropositivity like 3 electron can be donated by things like rare earth materials like yttriums, etc. As we travel towards the right side, we are getting lesser and lesser electropositivity. So, in that way we will come all the way up to, you can say, up to this region more or less, the zinc, cadmium, etc., where we can always get some amount of electropositivity. Beyond that, it becomes more and more, you will see the materials will become less and less active, and particularly we will gradually go inside the domain of the transition materials. For example, here we have a good group of transition materials, and beyond that you see the reverse phenomena. For example, this group, okay, oxygen, and then you have the sulfur, okay, or all the other rare earth materials, they can accept oxygen, they can accept electrons, like 2 electrons they can accept. Okay. So, they are electronegative, of course not very high. The higher degree of electronegativity you will find in terms of for example, this group where the halides, most of the halides are there, like chlorine, bromine, iodine, etc. So, they can readily become electronegative. And then you have the last group, which of course has they are inert gases, that means their outer layer is full of that magic 8 number of electrons, and hence they are neither electropositive nor electronegative. The periodic table also tells you through the color, you can check that which are the metals, okay, up to what distance you are going to get metals. For example, somewhere up to this range you are going to get the metals with you. Okay. So, and then which are transition materials, intermediates, neither metals nor non-metals, okay, boron, silicon, arsenic, selenium, all these things. Okay. And then you are getting perfectly non-metals, which are like, you can say, see these which the materials which are perfectly non-metals. So, thus periodic table gives us a fairly good idea about how to classify the materials in terms of their valency structure, metals and non-metals and intermetallics. Now, let us try to look at two important issues. The two important issues in terms of atomic bonding are, of course, the number one is the interatomic bonds, okay, and this is something like how much of force is acting between the atoms, so that they can hold together and act like a spring. Okay. So, something like a spring analogy you can bring in this case, particularly if you look at many of these bonds like ionic bonding or covalent bondings. And then the other issue is the atomic packing. This signifies the way in which the atoms are packed together, because okay, fine, there are these atoms which are bonded or hold together with the help of some kind of a spring, let us think of it. But these springs, we need not think is just a unidirectional in nature. Okay. Depending on the atomic packing, okay, we will see more of these various types of possible atomic packing. So, we will discuss about the crystal structure, but depending on the atomic packing, okay, so there are these directionality that will come, okay, in these springs, and that also, for example, affects the material properties of the system. So, here we will talk about two types of bonds, that the primary bonds, which are actually very powerful bonds. Okay, they are if you can see in terms of the melting or breaking of the bonds, something like 1000 to 4000 Kelvin. So, that is why they are very, very strong bonds. And there are secondary bonds, which are like van der Waals bonds or hydrogen bonds. They are relatively weak and they melt between 100 to 500 Kelvin. So, these are the two groups of bonds, the primary bonds, which has the ionic, covalent and metallic bonds, and the secondary bonds, where we will mostly consider van der Waals bond and hydrogen bonds. So, let us look into these bonds now more carefully. Okay, so, first we will talk about the ionic bonds. Ionic bonds are found in compounds that are composed of both metallic and non-metallic elements, because you need to have one highly electronegative or say electronegative and one electropositive in order to make a ionic bond. So, hence you will get compounds that will have a metallic part and a non-metallic part. Okay. So, for example, you consider sodium chloride. Okay. You have sodium as the metallic part and chlorine from the non-metallic part. Similarly, argentum chloride, cesium chloride, zinc sulphide, calcium fluoride, lithium fluoride, okay, or magnesium oxide, aluminum oxide, invariably you will see that one from the metallic part and one from the non-metallic part. Yes, one important thing on the ionic bonds are the oxides, for example. Okay, many oxides are there, which actually are formed because of the high degree of electronegativity, or so to say because of the high degree of reactivity of the metals with oxygen, and hence there are abundant forms of oxides, and these oxides sometimes has single oxide, or sometimes as we call that perovskites and many other forms. So they actually form good part of the minerals from which we actually extract through the process of mechanical and chemical processes. Through a series of that we extract the metals. So that is very abundant, the oxides, okay, and that is very typical of a ionic bond. Now these ionic bonds, they require definitely electron transfer to achieve stabilized outermost electronic configuration, and the bonding forces are actually coulombic and the attraction between the opposite charges. Okay. So let us say one of the examples, let us go through it. Okay. So this we are talking about the ionic bonds in sodium chloride. Okay. Now sodium atom, as I have shown you in the periodic table earlier, that they can very easily give up one electron, okay, and chlorine can accept that electron. So sodium atom transfers its valence electron, absorbing about 5.14 electrovolt of work to a vacant position in a chlorine atom, and that will release about 4.02 electrovolt of energy. So the network that will be done if you want to take one electron from sodium, okay, making it sodium positive, and if you put one here, okay, in the one of the vacancies in chlorine, then the network that will be done is the difference between these two, okay, 5.14 electron volt you are absorbing and 4.02 volt you are releasing. So the difference is 1.12 electron volt. That means you have to do some amount of work, okay, even though there is an affinity. If you keep one sodium atom very far away from the chlorine, it would not actually it would not be able to form the bond, because you have to supply this 1.12 electron volt in order to make this bond possible. Now what will make this bond possible? Okay, so if you look at that, the moment sodium is ready to give up this electron and chlorine is ready to take it up. So let us say that through some kind of a journey, this chlorine and the sodium are coming together closer and closer. So then as they are coming closer, the coulombic force will come into action, and this is something very much similar like other forces like electromagnetic forces, and where the force actually varies inversely with the square of the distance of separation between the two elements of opposite charges. So naturally beyond a certain distance this force is very weak. So as they come closer and closer, depending on the valencies of the ion types and the electron volts for each one of them, this is basically the Q1 Q2 replaces the Q1 and Q2. So this is Q1 and this is Q2. Okay. So that is the Coulomb force by definition. So they actually becomes more and more significant. Okay. Now you can also calculate that what is the work that is being done for bringing them from infinity to R by integrating this force F with the distance dr for each unit advancement of dr, and if you integrate that you will get this q square over 4 pi epsilon 0 r, okay, where this q square is nothing but q1 times q2 actually. So q square here is nothing but q1 times q2. Okay. Now you will be able to actually find out that what is the total energy that is there in the system. Okay. So, initially you need Ui, that is this your 1.12 electron volt of work, and then as it is coming closer and closer, this attractive force is giving the energy of q square by 4 pi epsilon 0 r that comes into picture. Okay. So, that is getting reduced from Ui. Also there is a limit of it. If you think of it that it is coming closer and closer together, it will never happen that one is going to collapse on the other. So, there is at the moment these two are coming very close, then their nucleus which are positive, they would start to actually so after penetration of the electron clouds, they will start to have a kind of a repulsion. So, that repulsion is actually modeled by a constant divided by r to the power n, where the n is approximately 8. So, that is what gives us the total energy in the system. Now, one can show actually that from the minimization of the energy point of view, about 0.28 nanometer range, you will see that the minimum energy comes to the system, which means it comes into an equilibrium. Okay. So, that is what is very important for sodium chloride bond to become stable. Now, you can see another interesting thing here, that sodium atom radius is 0.19 nanometer to begin with, but the moment and the chlorine atom radius is about 0.08 nanometer to begin with. But the moment sodium actually gives up the electron from the valency cell, then it shrinks, it becomes actually 0.10 nanometer, and chlorine becomes, its electron cloud increases, it becomes about 0.18 nanometer. So, as far as the ion is concerned, chlorine ion is actually bigger than the sodium ion. Okay. And as far as the atoms are concerned, sodium atom is actually bigger than the chlorine atom. Okay. So, that is what happens because of the exchange of the electrons from one to the other. Okay. Now, so this picture which I have shown for sodium chloride, let us try to understand this picture from a generalized energy point of view for a ionic bond formation. So, here we have the distance r as the x axis, okay, and the for moving the atoms, and u as the energy that is there in the system. And I already told you that the bond will be stable at a point where this energy is actually minimum. Okay. So, the minimization of the energy point of view, and here we will only consider interaction between two atoms, just to keep the whole things very simple. So, in one hand we have these separate ions here, sodium plus chlorine, okay, and they have an internal energy already, like we said that the Ui in this case was somewhere like 1.12 electron volt. So, that is what is the Ui, the initial energy in the system. So, that is where the whole system is starting its journey. Okay. So, where basically the sodium and the chlorine are very far away. So, that is where they are very far away, okay, and then they are coming closer and closer. So, as they are approaching the radius, the distance between the two, okay, so r is the distance between the two, that is actually coming down, okay, and as it is coming down, you can see that this is how the energy, the attraction energy is increasing exponentially. But I also told you that these two atoms will never collapse with each other. Why? Because beyond a certain point, somewhere here, you would see that there is a repulsion curve that will come into picture, okay, because the atoms will then start to repel each other, and that also expands exponentially at a much faster rate. So, hence if I superimpose these repulsion over this internal energy plus the attraction, the energy due to attraction, okay. So, we have Ui, we have the attraction part and we have the repulsion part, then we get this kind of a net energy curve. and that net energy curve has a minima, you can see it, right. So, because there are these two counteractive forces working, and that minimum point is where the bond becomes stable. So, for each and every combination of electropositive and the electronegative atoms in an ionic bond formation, you can find out what is this distance where the bond becomes very, very stable. Okay. So, that one can actually calculate, and generally it is in the nanometer level. When we talk about equilibrium in terms of the ionic bonding, I can give you an analogy that suppose you consider that you have three such atoms, okay, atomic positions. Now, there exists in kind of a stable position if a fourth atom is going to come in between. As you can see, if I just keep it somewhere, here they are going to collapse. So, these are all unstable locations, but there is a stable location which is stable because all the forces exactly balance at that location, and you will not be able to get any further collapsing. So, which actually says that this is the minimum in terms of the energy, the total energy if you consider in this system is the minimum point in terms of the energy, and hence this reaches the stability point. So, this is through a very simple students, the kids of our Shiksha Shopan students, they are very simple equilibrium of magnetic systems, you can actually explain this concept. Now, the overall properties that we can talk about it from the ionic bond perspective is that they are non-directional. Why they are non-directional? Because these are the two ions and they can get attracted from any direction. Okay. So, if we consider one positive and one negative, they can get attracted either any of the ways, right. So, from any of the directions they can come. So, that is one important property, that ionic bonds are non-directional. Okay. So, which actually can give some kind of an isotropic property. Some of the isotropic properties we can kind of guess that will come wherever there is ionic bond predominantly. They have high melting point. Okay. Why? Because there is the bonding energy in ionic bond is pretty high, something like 600 to 1500 kilojoule per mole or 3 to 8 electron volts per atom. So, it is very, very high, and hence you need lot of energy to break this bond, which means that they will be having high melting point, and also they are often very hard. Okay. So, that hardness is also coming because the bond is very, very strong, and that hardness may also result in terms of brittle materials, which we will see later on, that many times the hardness and brittleness are found together, particularly in the context of ceramic materials. Now, also we have to note that they are good insulators. Why? Because they do not have almost any free electron available with them. That's all electrons from one to the other is already gone inside the bond. So, hence they are good insulators in the solid state, but the reverse thing happens when they are in a dissolved situation or in a molten state, because then the ions are actually getting separated, and which means that they become good conductors of electricity, okay, in the molten state or at the dissolved state. So, that is the property of an ionic bond. Now, let us go to another important interatomic bonding, that is called covalent bonds. These covalent bonds are stable electronic configurations which are obtained not through these electropositive and electronegative attraction, but through the sharing of electrons between the adjacent atoms. Okay. So, naturally this sharing cannot happen from any direction. This is actually directional in nature. Covalent bond is directional in nature. So, that means the materials which will show this high covalent bonding, they can also show an isotropy in principle, and the number of covalent bonds in a particular atom actually depends on that from that 8 in the valency shell minus n, what is the number of valence electrons, that many actually there is the capability to absorb that many number of electrons into the system. Now, there are couple of materials which are very famous for covalent bonding. Okay. Of course, there are non-metallic molecules, hydrogen, fluorine, chlorine, etc. Then we have these molecules containing dissimilar atoms, CH4, H2O, HNO3, etc. We have the elemental solids, for example, carbon forming a covalent bond, or silicon or germanium. We have solid compounds like gallium arsenide, indium antimonide, silicon carbide. Okay. And we have some polymers which have some primary bonding, but they also contain secondary bonds. That is why polymers are not very strong, because they also contain the secondary bonds. So, what is the nature of this covalent bond? Let us look into one particular example, like say hydrogen. So, hydrogen, it has one electron to donate from the periodic table we have seen. Suppose two hydrogen atoms are agreeable to share one electron each, then you get a hydrogen molecule, okay, where the shared electrons are actually paired between both of them. If you think of another example, so this is between the same type of atoms, but two dissimilar atoms, then you see that carbon can actually absorb 4 electrons. Okay. So, hydrogen can give 1 electron can share. So, 1 pair, 2 pair, 3 pair and 4 pair. That is how CH4 or methane is formed. Okay. So, between the sharing of 4 hydrogen atoms with 1 carbon. So, that is between 2 dissimilar atoms. Another example is actually diamond, where carbon is sharing electron with another carbon, but that is not in any arbitrary way. Only when this kind of a tetragonal packing comes into picture, this tetragonal packing, okay, then only this is happening, and this is one of the strongest bonds available in any material, available in nature, and this is because the number of covalent bonds here is very high. Of course, it is highly directional, which means it is strong in a particular direction, but this the bond energy is very high, and hence diamond has the highest melting temperature, it has the highest thermal conductivity, okay, and also it has one of the highest hardness also. As you have seen in the hardness scale, we have shown diamond to be one of the hardest material. That is because this tetragonal structure, which is having maximum number of covalent bonds possible per unit cell, and that gives a very large strength, interatomic strength, and hence it becomes very hard. That is why diamond is used in applications such as cutting tools, polishing wheels, precision bearings, etc. So, for quite some time there was almost no material to challenge this, unless at a particular point of time we obtained carbon nanotubes, then only diamond could be challenged, because carbon nanotube has comparable or even better properties. Now, for a covalent bond, the story is not exactly the same, because you do not have any initial energy, because you are actually sharing. So, you have one energy due to attraction and one energy due to repulsion. Okay. The repulsion starts at a much smaller length scale, but here also you get this net diagram, and hence you get a region actually where you can expect the bond to be stable. And the expression is somewhat similar, except that you do not have any ui here, and you have a m here and a n here, and m and n value varies between 5 to 12. So, when m is less than n, then it is the attraction prevails, and when m is greater than n, then it is the repulsion that prevails. So, that is how the combination of attraction and repulsion creates a stable bonding. The important points then about covalent bonds are that very few compounds exhibit pure ionic or covalent bonding. That is why you will always get a mix of it, and usually you will get partially ionic or partially covalent bonding. If there is more difference in electronegativity between two atoms, ionic bond will predominate, and if there is a small electronegativity difference, covalent bond is going to predominate. the percentage ionic character of a bond between elements A and B, you can actually, if you know the X A and X B, the electronegativity, you will be knowing that what is the ionic character percentage of the bond. So, if it is smaller, then it is the covalent dominating, which means it will be directional. If it is not, then it will be ionic, which means it will not be directional. Now, other than these bonds, of course, there is another primary interatomic bond, which is also known as the metallic bonds. For metals, this happens in a somewhat different manner. Every metallic atom is ready to give up some of the electrons and form a general pool of electrons, which is also sometimes known as an electron cloud. So, you can actually define a metal to be something like, the core part, which is positive, each one of them. Okay. So, it gets ionized inside, and then that it is having a glue of electrons which are all around it, the free electrons which act as a glue across all the ion cores. So, that is what makes this kind of a metallic bonding. Okay. So, this imparts properties such as a high strength, malleability, ductility, luster, conduction of heat and electricity, because you have many free electrons available. So, you get actually conduction and good conduction of electricity in the system. And also you get a good bonding. Why? Because you have these the positive cores which are glued by the electron clouds. So, you get a good bonding via these electron clouds. Okay. So, that is what makes the metallic bonding. Then we have two other interatomic bondings, which are actually secondary interatomic bondings. These are one of them is called van der Waal bonding. Here also you have the charge positive and the negative charge responsible for the bonding, but this does not come from the atoms, it rather comes from the combination of atoms which creates a dipole. So, there is a dipole-dipole interaction, positive and negative dipoles, which creates this van der Waals force. And if this specifically happens with respect to hydrogen, then these are also known as the hydrogen bonding, which has dipole-dipole interactions because of the hydrogen positive attracting the OH minuses or similar things. And this happens in, for example, water, and that is why it expands upon freezing, because it is that kind of a very weak bond is found when the water actually freezes. Okay. So, in fact, that is why you would see that ice has actually lower density than liquid water, because at that time the hydrogen bonds form, and that gives the density, that gives a very low density to the system. Okay. So, that is one typical example of a hydrogen bond, but by and large both of these bonds are actually very weak. You can see, for example, the energy here is something like 10 kilojoule per mole, which is quite an order of magnitude lower than the ionic or the covalent bonding. So, let us summarize the whole thing now. That means, we have talked about the ionic bonds, and this is particularly for the ceramics, which shows ionic and some amount of covalent bonding, and that characterizes the high bond energy, high melting temperature for the ceramics, large elastic modulus, and very small coefficient of expansion. For the metals, which has a different kind of bonding, it is somewhat ionic in nature, but it is not between dissimilar atoms, but in the same atom itself. So, there you will see that the bond energy varies, although it is not so high as the ceramics, but it is still significantly high, and that is why you get a moderate melting point temperature, slightly lower than the ceramics, moderate modulus of elasticity, and moderate coefficient of expansion. Now, so the coefficient of expansion here is of course higher with respect to the coefficient of expansion for the ceramics. Finally, we come to the polymers. They have directional properties, because they have some amount of this carbon-carbon bonding, which are actually directionally strong, and they also have secondary bonding. It varies, but generally if the secondary bonding dominates, then you get a small melting point, temperature, small modulus of elasticity, and you get large coefficient of expansion. So, that much we can actually predict from the atomic bonding of these various types of atoms. Thank you. In the next class then we will talk about the crystal structure, okay, where we will discuss about crystalline solids, amorphous solids, unit cells and cubic structures. Thank you.